All right, so now let's go through some examples. The method is not specified, so I'll try to do each example in a couple of ways to kind of just see how it works with Venn diagrams, membership tables, with the definitions. So let's look at this one. So prove that A intersect union B and C is A intersect B union A intersect C. So this is like the distribution law. All right, so let's do it with the definition first. Okay, that's the hardest one. All right, so I'll try to do a few with the definitions so we can sort of see how it goes. So step one is to show that the first expression is a subset of the second expression. So we start with saying that X is a member of A intersect B U C. Right? Okay. So now we're going to look at this intersection right here. So by the definition of intersection, that means that X is in A and X is in the union BUC. Okay, so this is the definition of what intersection is. And now we're going to look at the union, split that up. So we have X is in A and X is in B or X is in C. So that's the definition of union. Okay, so notice now that I have three propositions. So once you kind of do this, this becomes propositional calculus. It's the laws that we were doing before. So this, if you can think of this as P and Q and R. So what I wrote here is that P and Q or R. Oops, that's an or. Well, I know propositional calculus. I know that this I can distribute to make it into, this is equivalent to P and Q or P and R by distribution. All right. So I can use that law in here. I can say that I have X is in A and X is in B, or X is in A and X is in C. Okay, so this is using the distributive law. Okay, so now we're going to turn things back into sets. So X is in A and X is in B means X is in A intersect B, or X is in A and X is in C means X is in A intersect C. So this uses the definition of intersection. Okay. So this means that if X is a member of this set or that set, X is going to be a member of the union of those two sets. Let me put this in parentheses right here, and this is the definition of what a union is. Okay, so basically I saw that I start with a member in this first set, and I showed that it also has to be a member in the second set, so that proves the first set is a subset of the second set. All right, so now let's do step two. We're kind of working backwards. Let me pick another color. So step two, we're trying to show that A intersect B union A intersect C is a subset of A intersect B union C. Okay. So similar, kind of just taking the steps backwards, we're going to start with our X, our arbitrary element, being a member of this set right here. Okay, and then we're going to use the definition of a union to say that X has to be in A intersect B, or X has to be in A intersect C. So that's the definition of what a union is. All right, now we're going to use the definition of an intersection and say that X has to be in A and X has to be in B, or X has to be in A and X has to be in C. All right, that's the definition of intersection. All right, now we're going to use the distributive law backwards. So if I have P and Q or P and R, then I can pull out the P. So X is in A and X is in B, or X is in C. So that's the distributive law. Okay, so now we're going to basically change things back into sets. So we can change this into a union. So we can say X is in, let's see, which order should I go? Yeah. X is in A, and X is in the union of B and C. So that's the definition of a union. And now change that to an intersection. So X has to be in A intersect with B union C. So that's the definition of intersection. All right, we're going to start with X as an arbitrary member in the first set. I showed through these steps that that X also has to be in the second set. So because all elements in the first set are in the second set, the first set is a subset of the second set. So these combined steps, step 1 and step 2, shows that these two sets are equal. Okay, so the final conclusion from those steps is that A intersect B U C has to equal A intersect B union A intersect C. All right. So yeah, that's long. You're right. Okay. So let's see. Let's look at this other ways. Okay. So I'm not going to do a membership table for this one because I did one for a very similar, another sort of distribution of sets problem. But let's do a Venn diagram. Right. So I want to do a Venn diagram for this first. Okay. So let's have 3 sets. A, B, C. In a universe. Okay, so I want BUC first, so I'm going to shade that. Let's do green. Okay, let's shade BUC. BUC is going to be the union of B and C. There we go. This right here. Okay. And now we want the intersection of A with BUC. Okay. So I'm going to draw another picture. You can kind of see what's going to happen in the same picture, but let's draw another picture. Okay, let me get back to blue. ABC. So if I take the intersection of the green with A, we see that that region is these kind of two slivers right here. Okay, so I'm going to shade that in like that. So intersection is going to be this. Okay, so this right here is BUC, and this right here is A intersected with BUC. Okay, so we're going to stop there and look at the other side. Okay, so we're going to look at AUB intersected with AUC. Okay, so let's draw diagrams. I'm going to draw a diagram for AUB. 1, 2, 3 sets. A and B and C. let's shade pink. I like pink today. So A union B is going to be the A and B circles. Everything in the A and B circles. All right, cool. Now let's draw the AUC diagram. So we have A and B and C. All right, and now I need to shade. Oh, I like this color. It's pretty. All right, everything in A and C. Okay, there we go right here. Okay, cool. So now we need to put these together and find the intersection between these two. Okay, so again, this is AUB, this is AUC. So the intersection, imagine put them on top of each other, what's common, right? So what's going to be common is that sliver right there. So let's redraw it. A and B and C. Okay, so I can see what's common between those two sets above is this region right here and this region right here. This is A and B intersected with AUC. All right, now you compare and you say, oh, it's the same picture. That means these two sets are equal to each other. Okay, that's the Venn diagram for this problem. All right, let's look at another example. Okay, so example 6, we want to prove that A minus C intersect with C minus B is the null set. They have nothing in common. Right, so I'm going to show it both ways again. Let's show it the membership table. And then we'll show the Venn also. Okay, so membership table, I notice that I have 3 variables. I have A and B and C. Oh my god, my lines are awful. Okay. And I'm going to pick the regular things. 1, 2, 3, 4 ones. 1, 2, 3, 4 zeros. 1, 1, 0, 0. 1, 1, 0, 0. 1, 0, 1, 0, 1, 0, 1, 0. Oh my god. A minus C. Okay, so let's see what that means. So A minus C means that the element is in set A, but not in set C. Okay, so if you're comparing ones and zeros, let's see, so I have 1, 1. That means the element is in both sets. So A minus C is going to be 0. Okay, so if the element is in both A and C, it's not going to be in A minus C. Now 1, 0 is going to be a 1, because 1, 0 means the element is in A, but it's not in C. Okay, so that fits with what the difference is. So basically, the only way you get 1s for A minus C is if A is 1 and C is 0. Otherwise, you get zeros. Okay, so we have 0, 1, 0, 1, and all these are zeros. Okay, now we're going to do C minus B. Okay, so C minus B, to get a 1 here, you have to have a 1 in C and a 0 in B. Otherwise, it's zeros. So 1 in C, 1 in B, that's a 0. 0 and 1, that's a 0. 1 and 0, that's a 1. 0, 0 is a 0. 1, 1 is a 0. 0, 1 is a 0. 1, 0 is a 1. 0, 0 is a 0. Okay. So now we're going to do A minus C intersect with C minus B. So in intersecting these, so we get 0, 0, 0, 0, 0, 0, 0, 0. contradiction. Okay, so basically this means it's the null set. So there are no elements for which that are going to be in the intersection of these two sets. Okay, so it's a contradiction. All right, so that proves it. All right, now let's do with Venn diagrams. All right, so we're going to draw our ABC in our universe. Again, I'm going to try to show steps. So first, A minus C. Okay, so A minus C is whatever is in A but not in C. Okay, so whatever is in A but not in C. So we're going to show that. That's right here. All right, cool. And now we're going to do C minus B. So I'm going to do another universe. And BC. Okay. Cool. And we're going to shade C minus B is whatever in C but not in B. All right, now we're going to find the intersection of these. Okay, so let me make some notations. So this is A minus C. This is C minus B. And we're going to try to find the intersections here. And if I look at these two pictures, I notice that these shaded areas don't overlap. That means the intersection is going to be the null set. So A minus C intersects C minus B. 13 is a B, is the null set. All right. Okay, let's see here. All right, so this is the last example in this section. Let's prove that A intersect B intersect C is a subset of A intersect B. So let's do it by Venn first. Let's have three sets here, A, B, and C in the universe. Right, so I'm going to draw the intersection of A and B. Right? And I'll be lazy and right on top of it, I'm going to draw the intersection of A and B and C. That's going to be in here. All right, so I can see that the blue, which is the intersection of A and B and C, is inside. It's a subset of the intersection of A and B. Okay, so that's the Venn diagram proof. Now let's do it by definition. Let's get another definition proof in here. All right, so here we're not proving equality, we're just proving that the first one is a subset of the other. So there's only step one. Okay, so we only need this one because we're just trying to show this is a subset of the second. All right, so we're going to start with X is a member of A and B and C. And by the definition of intersection, that means X is a member of A, and X is a member of B, and X is a member of C. So this is the definition of intersection. All right, so this is, let's group them this way. So X is a member of A, and X is a member of B, and X and X is a member of C. Okay. Again, think of this is just associative property. All right. So let's think of these as propositions. So this is like P and Q. Right, so we have conjunctive simplification. With the and, you can pull each of them off. So by conjunctive simplification, I can say X is in A and X is in B. Conjunctive simplification. Okay, so now turn this back into sets. So this means X is a member of A intersect B by the definition of intersection. Okay, so this proves that problem. So I start with X, an arbitrary member of this set, and I ended up with that X has to be a member of A and B. So this first set has to be a subset of the second set. All right, that's it.